Alrighty, so just a quick recap from last time. The whole purpose of this unit is essentially figuring out how we can identify the properties associated with a given system and state and how they're related to one another so that we can use them in our conservation of energy equation. So last time we talked a lot about, what constitutes a pure substance. Everything that we're talking about in this unit is only for pure substances, so you can only use it for those circumstances. So essentially, as long as you have a substance that has the same chemical composition, composition, I spelled that wrong last time, sorry about that. As long as you have a substance that has a chemical composition that's consistent throughout your system, that counts as a pure substance. So it's okay if it's in different states, as long as the composition is the same. Okay, we looked a lot at a bunch of different diagrams, but the key thing that really is consistent across all of them is that for what we're looking at, we care about these 5 states, and they are compressed liquid. So this is a liquid that's not close to vaporizing, a saturated liquid, which is a liquid right at its critical temperature and is about to vaporize, a mixture of saturated liquid and vapor. And then once that mixture is at a temperature where it's going to start to fully vaporize, then we get a saturated vapor. And then once the temperature goes beyond that point, we have a superheated vapor. So our tables look generally like this. We're going to do a lot of practice with these tables today, so you should get a pretty good handle on kind of how to use them and how to look at them. But let's see. Yeah, so when we're looking at diagrams like this, so right here is a TV diagram. They look similar for TS or TP, PV diagrams. We can switch out the quantities that are on the axes and they'll look generally similar to this. And so what we have is our compressed liquid on the left-hand side of that saturation line. Underneath the saturation line, which is our vapor dome, we have a mixture of saturated liquid and vapor mixture. And then on the right-hand side of the line, we have our superheated vapor, okay? So I think it's important to kind of keep this shape and what the states mean where you are on this graph in mind when we're looking at the tables, okay? Sometimes it's helpful. I remember when I was a student, I would do this just to like sketch this out and then draw my states on it, and that helped me avoid mistakes as you're working. So I will show you that as we go. Okay. Okay, so let's dive into our thermodynamic property tables. The basic concept behind the use of property tables is the following. So when we discuss TV, PT, and PV phase diagrams, we indicated that 2 independent properties are required to determine the other properties of a single compressible substance at a given state. And so the thermodynamic property tables are organized in the same way. And they look the same for any substance that you have a table for. So we're going to just focus on the steam tables. So these are tables for water. All right. So just understand that the process is identical. The format is identical. If you have a substance other than water, obviously the values will be different. Okay. And these tables, the tables for water and other substance are in the appendix of the textbook, and the heading will tell you what substance it's for. Okay. So before we begin, let's recall our rules for phase determination. All right, so I have here a TV diagram and a PV diagram. So when we're talking about the different phases, just to recap, we have our saturation line in blue. So this is our saturation line. And then we have our constant pressure lines here. So for example, this is a line of constant pressure. It's also called an isobar. All right, the points that are on the left-hand side and the right-hand side of our vapor dome or on our intersection with our saturation line, these give us VF of state 2. So this is P2 over here. It's kind of small. So if we say this is P2, and then on this side, we get VG2. All right, so in between VF and VG, this is a saturated liquid vapor mixture. And then on the left-hand side, we have the saturated saturated liquid line or saturated liquid state, and then a saturated vapor. So here is saturated liquid, and then this is saturated vapor. All right, anything to the left of this saturation line is going to be compressed liquid. All right, and then anything to the right is our superheated vapor. Any questions on the structure of a TV diagram? Kind of how to navigate around it, what it means for a state to be in different parts of that chart? Okay. Similarly, we have another plot that we look at, which is a PV diagram. So now instead of having isobars, we have constant temperature lines. So for example, we'll do T2 on this one as well. So this is an isotherm or constant temperature line. Line. That's T2. And then just like how we had on our TV diagram, we also have a vapor dome on this diagram underneath the saturation line. So the 2 points on this plot also give us VF2 and then VG2. Okay. Okay. Last but not least, a PT diagram gives us, and this is all for water. All these plots are for water. Okay, so this gives us our saturation pressure and temperature. So if, for example, we are at this location, we connect our saturation temperature with the saturation pressure. Okay. And then depending on where we are, we can know what state that we're at as well, right? Depending on each region. Okay. So we have 3 categories of thermodynamic tables that are going to be connected to what state we're in. So the first one is called a saturated liquid vapor table. We also have I organized my notes differently. We also have saturated vapor tables. And then finally, we have our compressed liquid table. All right, so essentially, if you recall our TV diagram, this is our saturation line. we're essentially separating the tables out into the three different phases that exist in this plot here. So our saturated liquid vapor table is going to tell us about anything inside of the vapor dome. Our saturated vapor table is going to tell us about things happening on this side. So on the vapor side, and then our compressed liquid table is of course the stuff to the left. Does that make sense? So this is why it's important to understand what state you're in so you know which table to be using, okay? Okay, so we're gonna do these one by one. And we're gonna start with the saturated liquid vapor table. In the book, this is tables A4 and A4E, as well as A5 and A5E for water. So just a reminder, the E at the end just means English units. So it's all the same information as the table without the E at the end, but a difference of units, okay? So these tables are organized by temperature or by pressure. And they list the saturated liquid and saturated vapor properties of the substance, as well as the saturation pressure or saturation temperature. Okay, so let's have a look in here. So this is our temperature. This is again for water. So up at the top of the table, it'll tell you the substance that it's for. So this one says saturated water. And then it will also designate that it is the temperature table. What that means is that this first column on the left is going to be temperatures. And then next to the temperatures, it will tell you what the saturation pressure is at that temperature. So if you remember on our PT diagram that showed us the states, those lines all give us what the saturation temperature and pressure are for a given state, okay? So let's put this in blue. So this is PSAT. All right, and then just like how we talked about last time, we have our four different quantities that we care about. So specific volume is here. We get VF and VG. Internal energy is U. Enthalpy is H, and then entropy is S. Okay, so for each of these, we will have quantities for the saturated liquid boundary right here. So these all correspond to saturated liquid. And then on the other side of the curve, we have our saturated vapor. Okay, and then for reference, we have that UFG is just equal to UG minus UF, and then that formula extends for all of the quantities. So HFG is HG minus HF, and SFG is SG minus SF. Okay? Okay. The table continues. I have them listed in the notes because our problems will need to use them, and so I wanted them to just be here for reference. But of course, they're also in the book, and then I have just the tables as a PDF on Moodle as well. So for reference for the exam, I will print off the tables and like staple it with the exam, so you have it. Okay. So one note here is at the critical point. So if you remember our TV diagram, we have our vapor dome that looks like this. And we have VF and VG for a given temperature. And then this point here is called T critical. All right, and at that critical point, we have that VF is equal to VG. UF is equal to UG. And HF is equal to HG. And SF is equal to SG. All right, so if we look at our table, if you remember that column that's looks like UFG, SFG, HFG, and then what one am I missing? U, H, and S. Okay, that's right. So these are all the difference between the saturation liquid value and then the saturated vapor liquid. So if those two values are the same, then these all become 0 at the critical point. So can anybody tell me on this diagram what temperature and pressure represent the critical point? Yeah.
337.95 degrees.
Yeah, perfect. Yep. Yep, so you'll notice that we have zeros in the FG columns. And then that happens because these two values are equivalent, right? So that means that this is the entry for our critical point. So T crit is 373.95. And then P critical is 22 kPa. No, sorry, MPa. Does that make sense? Okay. We also have this information organized in a pressure table. So again, that is shown to us right here. So we know that this is still saturated water is the substance, and then this is a pressure table. So essentially it's the same information, just organized a little bit differently. So we have pressure listed in our first column here, followed by saturation temperature. All right, and then all the other information is the same as before, or organized in the same way as before, okay? And it is just as long. And you'll notice that we have the same critical point entries. Okay. Okay, so let's use them, shall we? Okay, the first one is that we want to determine the saturation pressure for water at 50 degrees C. So do you guys think we should use the temperature table or the pressure table to figure this out? The temperature table, right? Yeah, great. So let's go to our temperature table. And we are looking for 50 degrees C. So first verify that we have the units that we want. This is in degrees C, so that looks good. All right, next we're gonna find the 50 degrees C entry, which is right here. So we are gonna be looking at this column or this row of data here. All right, and we wanna find P sat. What do we think? Yeah, so this is not too bad yet. We just have our PSAT in this column already. The temperature we want is already in the table, so this one's pretty straightforward. So our saturation pressure is just 12.35 kPa. All right, so let me just write this down. So since we're given T and we want PSAT, use the temperature table. And we get that PSAT is 12.352 kPa. Now, I mentioned that the pressure table has all the same information in it, right? So technically we could use the pressure table, but it will be more painful, right? So if we were to do that, then we would have to come up here and say, all right, well, I know the temperature and I want to find the pressure that goes along with this. So I would need to interpolate these two rows to figure out the pressure that corresponds to 50. Does that make sense? Can be done, kind of annoying. Okay, so it's best to go with the table where you have that information and start there. Okay. All right. Example number 2 is that we want to determine the saturation temperature for water at 400 kPa. So which table should we use for this one? Yes, we should use the pressure table because we're given pressure. All right, and we are going to look up at the entry for 400 kPa. First, make sure the units are in kPa, which they are, so we can look for 400 in here. So our entry is right here. All right, so our saturation temperature is just, we have to just consult the column that's called TSAT, and we get 143.61 degrees C, right? Any questions on these two examples so far? Does it feel pretty okay? It's not bad, right? It's okay. Okay. All right. We use these tables for a number of purposes. The first one is to evaluate saturation properties. So things like PSAT, TSAT, VF, VG, so on and so forth, as well as the properties of saturated liquid vapor mixtures. And then we also use them to determine the phase of a substance. Okay, so for a saturated liquid vapor mixture, we know that the pressure is PSAT at some temperature, and T is equal to TSAT at some pressure. Okay, so let's consider a saturated liquid vapor mixture of mass M and volume V. Our volume we can break into two parts because it's a mixture of liquid and vapor. So we can say that the total volume is equal to the volume of the vapor plus the volume of the compressed liquid, right? So we have volume of liquid plus the volume of the vapor. And we do the same thing for mass. So we have the mass, the total mass of our system is the mass of the liquid plus the mass of the vapor. And we can also rewrite this in just an algebraically reorganized way. So we can say the mass of our liquid is the total mass minus the mass of our vapor, for example. Okay. The liquid in the mixture has the properties of saturated liquid. So it's going to have all the properties of VF, UF, HF, SF. All right. And then the vapor in the mixture has all the properties of saturated vapor. So VG, UG, HG, SG. Okay. What this means is that the specific volume of the liquid is equivalent to VF. The internal energy of the liquid part of this mixture is equal to UF. H, the enthalpy of the liquid portion is equal to HF, and so on and so forth. And then the same thing for the vapor. So the specific volume of the vapor is equal to VG, and so on and so forth. All right, so does that make sense to everybody? We can kind of partition our mixture, and anything that's compressed liquid is going to have the properties of the compressed liquid at that temperature and pressure, and the vapor has the properties of a saturated vapor at that temperature and pressure. Okay. We are going to let V be an average specific volume of our mixture. So essentially we're saying that our mixture is going to be well mixed and our specific volume is just an average of what's happening in the whole system. So if that is the case, then we can rewrite our volume as our total volume is mass times this average specific volume, which is still the volume of the liquid plus the volume, excuse me, of the vapor. Where we can also rewrite these two terms slightly differently. So for the volume of our liquid, we can write this as the mass of our liquid times the specific volume of our liquid. And then the same thing for the vapor. So we have the mass of our vapor times the specific volume of our vapor. But if you remember, the specific volume of our liquid is VF and the specific volume of our vapor is always VG, right? So we can write this then as M liquid times VF plus M vapor times VG. Does that make sense? Everybody's with me? Okay, great. Now, it would be convenient if I wrote this equation in terms of just M liquid or just M vapor, and they're connected by the total mass of the system. So what I'm going to do is I am going to substitute this expression in for here. So I'm going to put that in here. And I get that M liquid is M minus M vapor. Oops. Times VF plus M vapor times VG. All right, and then just to remind you, the left-hand side is M times average specific volume. So this is still our average specific volume. All right, and I am going to do a little bit of algebra. So I am going to divide through by M. Which is the total mass. So I have that the average specific volume is equal to M over M, or N minus M vapor divided by M times VF plus M vapor divided by M VG. Does anybody recognize from last time this quantity by chance? This is what we used to determine kind of where we are between compressed liquid and compressed vapor under our vapor dome. So this is the quality. Remember X? So this is the quality of the mixture. All right, it just tells us essentially how much vapor relative to the total mass we have in our system. So this thing goes from 0 to 1. If quality is 0, then it's a purely saturated compressed liquid. And if it's 1, then it's a purely saturated vapor, right? Okay, so that means that this is equal to 1 minus X times VF plus X times VG. Now, this is only for a saturated liquid vapor mixture. All right, hopefully just the way this equation is written reminds you that, because we know that quality, so X, is undefined unless you have a mixture, okay? Okay, so this will be useful to us. And if we look at this equation, it's always good if you do a little derivation like this to check that this makes sense. So if our quality is 0, then that means that we have a completely saturated compressed liquid. So our specific volume should be VF, right, by definition. So if we plug in X equals 0 into this, we end up with VF. So that's good. And then if our quality is 1, that would mean that we have a completely compressed vapor, or saturated vapor, sorry. So if we plug in 1, we have 1 minus 1 times VF, so that goes away, and then we just have 1 times VG, so that checks out, okay? We can do a similar derivation, which I'm not going to show you, but it looks exactly the same as this. So similarly, we can do this for internal energy, enthalpy, and entropy. So we have U is equal to 1 minus X UF plus X UG. And H is equal to 1 minus X HF plus X times HG. And S is equal to 1 minus X SF plus X HG. Okay. These equations you might see written in slightly different ways, depending on what reference you're looking at, but it's just an algebraic manipulation of the same equation, okay? Okay. All right. So let's do an example. And the question is, what is the phase of 10 kilograms of water at 50 degrees C with a volume of 100 cubic meters? As a follow-up to that, we want to know what the pressure is and the quality if applicable. All right, so the quality we only have if we have a mixture, right? Okay, so let's write down what we're given. We are given that we have water, so that's good because those are the tables that I have reproduced for you in the notes, so that's convenient. We have that the mass is 10 kilograms. The temperature is 50 degrees C. And then our volume is 100 meters cubed. Okay, so from this, we can already find the specific volume because specific volume is just volume divided by mass, right? So our specific volume is volume over mass, which is 100 meters cubed divided by 10, which is just 10 meters cubed divided by kilograms. All right. So what we're going to do is we are going to determine our phase by comparing our specific volume to VF and VG at 50 degrees C. All right. So we will find the phase by comparing V to VF and VG at T equals 50 degrees C. All right, so essentially what we're doing is on our TV diagram, we have our vapor dome that looks something like this. And we're gonna find for T equals 50 degrees C, we wanna figure out VF and VG. And then based on where 10 meters cubed per kilogram falls on that line, we'll know what the state is, right? Or the phase is, sorry. So if we're to the left of VF, then we have a compressed liquid. If we're between VF and VG, we have a mixture. And then if we're to the right of VG, we have a compressed vapor. Does that make sense? Okay, so let's hit the tables. Should we use a pressure table or a temperature table? Temperature, right? We're given temperature. Let's use the temperature table. All right, so we want to find VF and VG. That's a pressure table. Here's a temperature table. All right, so I already have the 50 degrees C line highlighted here. So we have that VF is 0.001012 and that VG is 12.026. All right, so let's write that down. So VF is 0.001012 meters cubed per kilogram, and VG is 12.026 meters cubed per kilogram. All right, so this is 0.001012. Oops. Meters cubed per kilogram. And then VG is 12.026 meters cubed per kilogram. So where does RV stand on this line? Any thoughts? Yeah, closer to VG, but under the vapor dome, right? So we're about here-ish, right? So what does this mean? What is our phase? It's a mixture, right? So this is a saturated liquid vapor mixture. Okay. What about the pressure? We want to know what the pressure is. How would we figure that out? So I'll remind you, I kind of went over it very quickly. We're going to use this. That if we have a saturated liquid vapor mixture, our pressure is going to be the saturation temperature pressure at the temperature that we're at, right? Okay, so let's go up to our table that we were at before. So our saturation pressure for 50 degrees C is 12.352 kPa. All right, so that has to be the pressure of our mixture. So saturated liquid vapor mixtures have a pressure equal to Psat at that temperature, which from the table is 12.352 kPa. So this is from the table. That make sense so far? Okay. All right, last part of this question is, what is the quality if applicable? So can we define the quality for this? Yes, so it's a mixture, so we can do quality, right? So the quality is X, and that is defined as the mass of the vapor divided by the total mass. Okay. So what we have is that we're going to use the following relationship. So we can say that the volume of our vapor is the mass of the vapor times V of the vapor, which we know is Vg. So we have M vapor Vg. And we also know that the volume of the liquid is the mass of the liquid, oops, times Vf. And we used this before to find this expression. So our specific volume of our mixture is the specific volume of our fluid plus, actually, here, let me do the algebra for you. I won't skip a step. So I'm going to use this equation right here in the yellow box. So I have 1 minus X Vf plus X Vg, right? So I want to solve this for X. So I'm going to just reorganize the right-hand side a little bit. So I have Vf plus X times Vg minus Vf, right? So that means I can solve for X as V minus Vf divided by Vg minus Vf. And we have all of those values already, right? We looked them up or solved for them. All right, so our volume, our specific volume is 10. Vf is, where is it? 0.001012. And then VG is 12.026 minus VF, which is 0.001012, which gives us a quality of 0.83 or 83%. All right, which that makes sense. We drew our little red dot mostly to VG. If we were at the compressed vapor line, we would have a quality of 1, right? So that makes sense. All right, did anybody have any questions on the last example? I did get a good question from Allie, and it's worth mentioning. So we found our dot was under the vapor dome, so we were using the saturated liquid vapor tables, right? If we had found that the dot was on to the left of that vapor dome or to the right of the vapor dome, we would still use tables, but different ones. Okay, so we haven't talked about those tables yet, but they exist, and that's what you would do. Does that make sense? Okay, cool. All right, so let's do another example, a slightly different example. All right, so we have water again at 50 degrees C, but this time we are given its internal energy. So we have an internal energy of 2,500 kilojoules per kilogram, and we want to find the phase of that substance as well as the quality if applicable. All right, so we are given thank you. Nope, no more. Okay. We're given water. We're given that the temperature is 50 degrees C. And then we have that the internal energy is 2,500 kilojoules per kilogram. Right? Okay, so I'm always going to start off by drawing my TV diagram. All right, so sorry, not TV. We're going to do a TU diagram now. Right, so kind of the same idea as that last example that we did, but now instead of the specific volume, we're looking at specific internal energy. Okay, so the strategy is the same. We want to figure out for T equals 50 degrees C, where are we on this line? So we need to figure out UF and UG to figure out where our given internal energy is on this curve. Okay, make sense? Okay, so what table should we use? Should we use the pressure table or the temperature table? Yeah, we're going to use the temperature table because we're given the temperature. All right, so let's go back to our temperature table. That's the pressure table. Keep going, keep going. Okay. We're still looking at this 50 degrees C line. All right, but now we want to find UF and UG instead of VF and VG, okay? So we're looking at these values. Okie dokie. So let's see where our internal energy falls. So from the table, we have that UF is equal to 209.33 kilojoules per kilogram. And we have that UG is equal to 2,442.7 kilojoules per kilogram. So we have 209.33 here, and then 2,442.7 here. And this is kilojoules per kilogram. Okay, so where are we at with our internal energy of our substance? Yeah, so we're over here. So this is 2,500 kilojoules per kilogram. So what does that mean about the phase? Yeah, so this is it's actually a superheated vapor. So once we're off of the line, it's a superheated vapor. So since U is greater than UG at T equals 50 degrees C, this is a superheated vapor. What can we say about the quality? It doesn't exist. So this is undefined since it's not a saturated liquid vapor mixture. Does that feel okay for everybody? Yeah.
For it to be considered like a saturated vapor or a saturated liquid.
Yep.
Does it have to be exactly that number or could it be like slightly under?
It needs to be exactly that number. Yep. So you have to be exactly on the saturation line to be called specifically a saturated liquid or a saturated vapor. Otherwise, you're compressed liquid or superheated vapor or a mixture. So those are very, very special cases. Other questions? Yeah. Kilojoules per kilogram. Oh, yes. Thank you. Did I do that anywhere else or was that the only spot? Ah, I appreciate you. Thank you. Other question? Oh, yeah.
U equal GG, then it was U. Saturated vapor,
Yes.
and then the equal to that would be a saturated vapor.
Yes. Yep. Other questions? Okay. Okay, so next we're going to talk about our superheated vapor tables. So these are organized by pressure. So if you remember, pressure and temperature are independent properties. Dependent. Properties, so pressure and temperature are independent from each other in the superheated vapor phase. So in each pressure cell of this table, the four intensive thermodynamic properties are listed as a function of temperature. So we have our specific volume, our specific internal energy, specific enthalpy, and specific entropy. So to kind of explain what I mean by a pressure cell, so pressure cells are essentially these boxes that exist. All right, and you'll notice that at the very top of each of these boxes, we have a pressure. In the parentheses of each pressure is the saturation temperature. So this is our saturation temperature for that pressure. And then our properties that go along with that saturation temperature are shown as the first line. Okay, so organized a little bit differently, right? And in each of the blocks of different pressures, we have all of our values organized by temperature. Okay, so it's kind of like our previous table, but like squished down, and then we have it repeated a bunch of times for different pressures. Does that make sense? You'll also notice that we don't have VF and VG on this table, so we're outside of the pressure dome or the vapor dome for this data. So this is all superheated vapor at this point. So we just have one value for each of those four properties now. Okay. Okay. All right. So it goes on. This table goes on for a while. It's a big one. A very big one. Okay, so we will make use of those tables when we do an example. But first, I want to talk about what we do if the value of, for example, the temperature that we want to assess isn't listed exactly in the table. So if you remember before, we were looking at a temperature of 50 degrees C. That was really convenient for us because it was a line in the table. But we could have a problem where the temperature is 53 degrees C, right? So we're not just going to round and decide it's 50. We're going to actually compute all these things at 53 degrees C, which requires us to do interpolation, linear interpolation. So essentially what happens is that we want to decide what that value is we're looking for by assuming that the property slightly less and the property slightly above from it it's linearly dependent to them. So like, for example, if we wanted to have, if we have a temperature of 50 and then temperature of 40, and the T that we're interested in is 43, which is here. And then we want to find out the specific volume, right? For example, we would say, okay, we have our, I'll call this T1, V1, T2, V2. All right. And then we would say, okay, these two data points that we know, we're going to assume that they're connected with a straight line. So we would take our 43 and find where it is on that line. And then from that, we would be able to find our V3. Does the idea kind of make sense, what we're doing here? Have we done a linear interpolation before? Oh, okay, old pros. Okay, so basically what we do is we will do, we'll have three properties. So if we have two properties that are known from the table, and then we want to find the third property, what we'll do is we will say, so if we want to find information about X, Y, Z. So this is our unknown state. But we know X1, Y1, Z1, and X2, Y2, Z2. So these are the values that are above and below what we're trying to find. So these are known. What we will do is we'll say Y minus Y1 over Y2 minus Y1 is equal to X minus X1 over X2 minus X1 is equal to Z minus Z1 over Z2 minus Z1. And this should be X1. Okay, so essentially we're just saying the slope has to be the same, right? What this equation does is it says, okay, the slope that I have here, so this M from 1 to 2 has to be identical to the slope from 1 to 3. All right, if it's on a line, is essentially what we're doing. So let's just do an example so that we can practice this. So we want to determine the enthalpy H of water at 1 megapascal and 480 degrees C. So what we're given is that P is 1 MPa, which is 1,000 kPa. And we have that temperature is 480 degrees C. All right, so let's go to our original tables to figure out what state we're in. So we want to figure out, we want to find Tsat at P equals 1 MPa. So we will use table A5. So this is our mixture table, right? So let's go up there all the way to the beginning. No, too far. Okay, here. So we're given a pressure, so we're going to go to our pressure table. And we want to look up 1,000 kPa, which is here. All right, so our saturation temperature is 179.88. Degrees C. So to figure out what state we're in using that, we will look at our PT diagram. Which I'm just going to give you a cartoon sketch of what that looks like. So we have, for water, it's going to look something like this. So we've got liquid. This is P and T. This is vapor. And then this is solid. Okay, and it turns out that for P equals 1 MPa, this Tsat at P, this is 179.88. The temperature that we're given is 480, which means that we are way over here. Okay, so this means that we have a superheated vapor. Does that make sense? Yeah.
How do you know if you use a PT diagram?
So that's a good question. We're using our PT diagram because we are not given any other properties to use. Like if we were given the enthalpy or the internal energy or something like that, like with the other examples that we did, we could find, for example, UG and UF and figure out that it's above UG. But since we're only given P and T, we have to use a PT diagram. Does that make sense? Yeah.
How do you know, like, where the dotted line, the, pressure, 1 MPa, how do you know that, where that is
On the real one?
well, okay, I understand why it's like,
Hang on, let me go back to the actual picture. So this, this should have, for like a real substance, it would have actual values on it.
okay.
Yeah, it's not just like a generic curve like this. So in the book, it'll have numbers.
like numbers.
Yes.
I'm confused on the, like, the pressure, the vertical, and it's just like, how do you know, like,
Where to cut it across.
Yeah.
Yeah, so in, and I'll bring this next time, it should have numbers on there,
Okay.
like for, depending on the substance. Yeah, this one, I should have included a better one. This one, you know, it shows like the things that expand and contract on freezing. So it's just kind of like a cartoon of what a phase diagram looks like. Yeah. Yep. Other questions? Okay. Okay, so we know that we're in a superheated vapor, so we want to use the superheated vapor tables. And we want to find our enthalpy of water at those two conditions. So let's see what we have. So if you remember our superheated vapor tables are organized in pressure cells. So the first thing that we're gonna wanna do is identify our pressure cell that corresponds to 1 MPa. All right, so let's do that. So 1 MPa is this one over here. All right. And actually, we could have, since we just wanted to know the saturation temperature, that 179.88 degrees C is in here as well. So I guess I didn't have to scroll as far as I did, but you can find it in multiple places. Okay. All right, so we found our 1 MPa pressure cell, and our temperature is 480 degrees C, which should exist somewhere right here. Right? Okay, so we have temperature and enthalpy for 400 and 500, and we just need to interpolate it to find for 480. So let's do that. So I'm going to be making use of, let me see. I'm going to use 400 and 500, and then here are my enthalpies that I'm going to make use of. Those two guys right there. So I like to make a little table to keep myself organized when I do these types of problems. So from the table for superheated vapors, we have the following. So we have temperature in degrees C, and then we have enthalpy, which is kilojoules per kilogram. All right, and we have 400 in the table, as well as 3,264.5. And then we have 500, which is 3,479.1. And we want to find the value at 480. So I'm just going to call this H. Okay. So I'm basically going to make the argument that the slope between 400 and 500 degrees C is the same as the slope between 400 and 480. All right. Okay. So I have my first slope is 3,479.1 minus 3,264.5 divided by 500 minus 400 is equal to H minus 3264.5 divided by my temperature at H is 480 minus 400. Okay, so what I have here is I have my points at 400 degrees. So that's this and this. And then I have my points at 500 degrees C, which is this and this. And then I'm trying to find these guys, which are here and here. Does this make sense? Feels okay for everybody? So when you're doing the second part, I technically could have also done 3479 minus H divided by 500 minus 480. That's fine, but then I have another like minus sign to deal with because I have a minus H. So it's just quicker algebraically to do it this way, but you'll get the same answer either way. Okay. Okay. So when I solve this, I get that H is 3,436.2 kilojoules per kilogram. All right, I always like to kind of look back at that value that I calculated in terms of what's in this table. So I expect since 480 is closer to 500, I should be getting a value that's between the green and the red numbers, but closer to the red one, which it is. So it's a good little sanity check to do. Because sometimes if you make an error with the calculator or whatever, it's a very easy way to find out like, oh, I got 40,000. That's clearly wrong. So you can go back and fix it. Any questions on how to do that? No? Okay. Let's do another one. Okay, now we want to determine the temperature of water at 1 megapascal and an internal energy of 280, or I'm sorry, 2800 kilojoules per kilogram. Okay, so we have that pressure is 1 MPa, and we have that our internal energy is 2800 kilojoules per kilogram. What should we do first? Any ideas? Yeah.
Should check the superheated vapor table to find the saturation temperature at 1 megapascal.
So I like where your head's at. That's what we did last time. However, this time we're given an internal energy, not a temperature. So we need to find something we can, yeah, so now in order to find the phase, which is what you're getting at here and is correct, we want to find UF and UG and figure out where this U is in comparison to it. All right, so we're going to go back to our mixture tables to figure that out. Okay, so we will use table A5. So this is our pressure table for a mixture. I'm going to just start saying mixtures because it's really long to write, you know, compressed liquid / vapor mixture a million times. So we're going to use a pressure table for mixtures to find UF and UG at 1 MPa. Does anybody want to go ahead and do that for me? And I'm going to draw the PU diagram here. So essentially what I want to find is UF and UG. And then we're going to do this for P equals 1 MPa. Okay, so all the way back to, here's our pressure table. And we're at 1 MPa. So let's look at now UF and UG. All right, so I've got 761.39 on the left-hand side and then 2582.8 on the right-hand side. So let's write that down. Okay, so we have that UF is 761.39 kilojoules per kilogram, and then UG is 2582.8 kilojoules per kilogram. So where are we at on this PU diagram? Yeah, we're above UG. So we're in our superheated vapor. So the justification is that U is greater than UG. So this is a superheated vapor. Does this make sense so far? So our first step is always going to be to figure out the state, and then we know what table to use to find the property we're looking for. Okay, so now this means that we can go to our superheated vapor table, and we want to look for the pressure cell for 1 MPa, which is the one that we highlighted last time because we were at 1 MPa again. All right, and we're given that the internal energy, right? And it's 2800. So we want to look in this column. So this is our internal energy column, and chances are there's not going to be an entry for 2800 because that would be far too convenient. But we have two entries that are pretty close. All right, so we've got these two. That top one is 2793, and then the bottom one's 2875. All right, and so we know that these corresponding temperatures are 300, 350. So we expect to get a temperature somewhere between those two values. Okay, so let's do our interpolation. All right, so we have temperature and then internal energy. And we've got our values between 300 and 350, and then we want to find T. Our internal energy for 300 is 2793.7, and this is kilograms per kilojoule. Our temperatures are in degrees C, of course. 2800 is our internal energy for the temperature we're looking to find. And then 2875.7 is the internal energy at 350. Okay, so let's do our interpolation. So we're saying that 2875.7 minus 2793.7 divided by 350 minus 300 is equal to T minus is equal to 2800 minus 2793.7 divided by T minus 300. All right, and so we find that T is equal to 303.8 degrees C. That's a decimal place. All right, so just as a sanity check, we look back on our information that we put in that little table there, and we notice that 2800 is very close to that entry for 300. So a value of 303.8 makes some sense, right? Okay. I have one last example that we're going to do in class today. However, I want you guys to form into little groups and try it yourselves. Yes. Oh, wait, what? Oh, yes. Those units are going to be the end of me today, apparently. Thank you.